So it turns out that the type of bond it forms depends on the difference in electronegativity between the two atoms that form the bond. So a difference in electronegativity here is represented as delta L neg. And if we look at this chart on the right, it shows the different types of bonds and the difference in electronegativity between the two atoms that form the bond. Ionic bond. So two of the bond types that we discussed previously are ionic bonds and covalent bonds. On this chart, the ionic bond is at the right. So if we have a difference in electronegativity of 2 or greater, we have an ionic bond. If it's less than 2, we have a covalent bond. However, here we distinguish two different types of covalent bonds. We have nonpolar valence when the two atoms have a very similar electronegativity. And then we have polar covalent bonds when there's a fairly large difference in electronegativity, not quite large enough to form an ionic bond, but larger than for a nonpolar covalent. So basically, even though we have these classifications, in reality, what occurs in nature is that we have increasing ionic character. So we have very ionic bonds, we have ones that are less ionic, and then we have some that are very polar covalent, less polar covalent, and then we have completely nonpolar. So let's take a look at some examples to explain what I mean here. So if we look at a compound formed between potassium, which is a nonmetal, and chlorine, potassium is a metal and chlorine is a nonmetal. Potassium has an electronegativity of 0.9 and chlorine is 2.9. You don't need to memorize these. These are in your book, and I will make sure that you have this information on an exam if you need it. So basically, if we subtract the electronegativity of chlorine from that of potassium, we get the difference in electronegativity is 2. And if we look at our chart here, 2.0 or above, that's a ionic bond, and which is what we would expect because potassium and chlorine are a metal and a nonmetal, and they form an ionic bond. So now let's take a look at a different example where we've got two different nonmetals, chlorine and bromine. Chlorine has an electronegativity of 2.9. Bromine is 2.8. So when we subtract these, we get an electronegativity difference of 0.1. So they're nearly the same. They're very close. And in the chart here, that shows us that this is a nonpolar covalent bond. When we talk about a nonpolar bond, what we mean is that the electrons are shared equally between the atoms. Then we have, so this is also sometimes called a pure covalent bond. So if it's a polar covalent bond, it has an ionic character, but it's not completely ionic. The electrons are shared, they're just not shared equally. And then I just also want to mention, we talked about this a little bit previously, but we'll show it again here. Since we're talking about electronegativity, when we name compounds, the less electronegative element is always written first in the formula. So this makes sense, right? Because if we have the metal always comes first. So, but even when we've got two nonmetals, the less electronegative nonmetal comes first. So when we have chlorine and bromine, even though they're nearly the same, bromine is slightly less electronegative, so it goes in front. So it's bromine monochloride is the name. So why do we do this? Well, basically, chemists wanted consistency in naming, and by coming up with this rule, ensured that people wouldn't write two different names in different publications, and makes it easier to know which particular compound you're talking about. So we have a example of a nonpolar covalent bond and an ionic bond. Let's look at another example, and this time we're going to use sulfur and oxygen. So sulfur's got a electronegativity of 2.5, oxygen's 3.5, so or 2.4 for sulfur. And basically, so when we subtract that, we get an electronegativity difference of 1.1. That's right in the middle, which means that this is a polar covalent bond. So just to talk again about the naming, so what this means is if we look at the electronegativity difference, since sulfur is less electronegative, it comes first. So it's sulfur dioxide is the name of this compound. And then also in the formula, it comes first. So sulfur always comes before oxygen in a formula. And again, this is just for consistency to make sure that we know what we're, so that everyone names the compound the same way. Next, we'll take a look at the relationship between polarity and molecular shape. We'll use carbon dioxide or CO2 as an example. So there's a carbon in the middle of this molecule and two oxygens. So we have a carbon-oxygen bond. Carbon has an electronegativity of 2.5, and oxygen has an electronegativity of 3.5. When you subtract these, you get a difference of 1.0. That's right in the middle in the region of polar covalent bonds. So that's the type of bond in this molecule. Now we're going to look at the shape of carbon dioxide. And to figure out shape, the best way to do it is to draw a Lewis structure, because that shows us how many electron pairs there are in the atom. So the shape of carbon dioxide is linear because it's got two electron groups, which are on opposite sides of the carbon atom. And so it's a linear shape. Now it's polar covalent bond, but if we look at the distribution of charges, we have a positive positive charge in the middle and a partial negative charge on each end of the molecule. However, because this is symmetrical, the positive charge is exactly in the middle. It turns out that the molecule is symmetrical and the charges cancel each other out. So when we have no uneven charge distribution across the molecule, it's called a nonpolar molecule. And this molecule is nonpolar, even though we do have an uneven charge distribution within certain bonds, the entire molecule is nonpolar. Now we'll look at a different example of water, or H2O, which has two OH bonds. Electronegativity of oxygen is 3.5 and hydrogen is 2.1. So when we subtract, we get a difference of 1.4. So that's right in the region of a polar covalent bond. So let's look at the shape of water. So this has a bent shape, and that's because of the two lone pairs of electrons push the hydrogens towards each other. So then if we figure out where the charges are, we have a partial negative charge on the oxygen, because remember it's got a stronger pull on electrons than the hydrogen does, and partially positive on the hydrogen. And because it's bent, the entire molecule is polar. So each water molecule behaves like a tiny magnet, so that the partial negative charge attracts positive charges. So water molecules are attracted to one another, and they're also attracted to other polar substances and to ions. Okay, I'm going to now describe how we can tell whether a molecule is polar or not. First of all, if we have bonds within a molecule that are nonpolar, the molecule is going to be nonpolar. So for example, bromium chloride, which I showed you earlier, there's a very little difference in the electronegativity of the two atoms. So that means that it's a nonpolar bond, and the entire molecule is going to be nonpolar. And this is true always if all of the bonds are nonpolar, because there's no uneven charge distribution anywhere in the molecule. Now, if we do have polar bonds within a molecule, the molecule itself may be polar or nonpolar. It depends on the symmetry of the molecule. So carbon dioxide is a symmetrical molecule. So that means that the bonds are polar, but the molecule itself is symmetrical, so it's nonpolar. And if we look here, the charges are distributed evenly across the carbon dioxide molecule. So essentially the positive charge in the middle is sandwiched between two negative charges, so that it's as if it is evenly charged, even charge distribution across it. Water, on the other hand, is a bent molecule, so that the negative charge on the oxygen and the positive charges on the hydrogen stick out. So this is a polar molecule. So it depends whether or not the molecule is symmetrical if it has polar bonds. So let's look at some more examples of molecules and determining whether they're polar molecules. Let's start with carbon tetrafluoride, or CF4. Fluorine is the most electronegative element with an electronegativity of 4.1. Carbon is 2.5, so when we get subtract, we get a polar electronegativity difference of 1.6. So from our graph, that is right in the middle, so that's a polar covalent bond. But if we look at carbon tetrafluoride, we have a carbon that's surrounded by 4 fluorine atoms. So this is a tetrahedral shape. This shows it kind of being flat, but it actually goes in different directions so that the 4 bonds are as far apart from each other as possible, but it is symmetrical. So basically, because the molecule is symmetrical, this is a non-polar molecule, even though there's a very strong polar covalent bond between the carbon and fluorine. Overall, the charge distribution across the molecule is equal, so it's non-polar. And now we'll take a look at ammonia, or NH3. Nitrogen has an electronegativity of 3.1, hydrogen's 2.1. So that difference is 1.00. Again, this is a polar covalent bond. But in this case, we have this trigonal pyramidal shape. And so basically the nitrogen has a lone pair of electrons that's pushing away the hydrogens, so that we have basically it's an asymmetrical molecule. And so there's going to be a partial negative charge on the nitrogens and a partial positive charge on the hydrogens. And because this molecule is asymmetrical, the whole molecule is going to be polar because of these asymmetrical charges. Okay, I'm going to show one more example. There's obviously many kinds of molecules, so there's in each case you have to look at the specific arrangement of atoms and electronegativity. So in this example, I have CClF3, so that's got a carbon in this central carbon, and there's 3 fluorines around it and 1 chlorine. So we have 2 different kinds of bonds. So the chlorine-carbon bond, the difference in electronegativity is 0.5. So it's considered polar covalent, but it's barely polar covalent. It's almost nonpolar. And then the fluorine and carbon, the difference is 1.5. So that is quite polar. And the shape of this molecule, or the electron groups arrange themselves as far apart as possible. That's a tetrahedral shape. So it is a symmetrical molecule. However, because there's 2 different kinds of bonds, it actually is a polar molecule. So there's going to be the fluorine is going to have a more negative charge than the chlorine. So there's an uneven distribution across the molecule. I'm now going to summarize the steps for deciding if a molecule is polar or nonpolar. Step 1, check if the bond or bonds within the molecule are polar by checking the difference in electronegativity using the tables that I showed and diagrams I showed you earlier. Step 2 is check if the molecule is symmetrical, and to do this you can use a Lewis diagram, and I'm also going to show you a program that shows molecular shape that will hopefully be helpful. And step 3, determine if a charge is evenly distributed across the molecule after you figure out its shape. And in regard to this, when we look at charge distribution, if the charge is evenly distributed across the molecule, it's nonpolar.
and if it's uneven, it's polar.